from Carnegie Mellon, who's going to tell us about abstraction functions as types.
All right, thanks, Ben. Thanks everyone for coming. I'm excited to tell you about some work that I've been doing with my collaborators Runming and Bob about abstraction functions as types, which is really a method for verification of data structures in dependent type theory that supports modularity. All right, so let me motivate this idea. I'm going to try to not say anything too abstract today, and I'm going to do that by using a specific example of queues. So just as a reminder, a queue is maybe a type that's equipped with an NQ, a DQ, and an NQ and a DQ operation, along with the way to start as an empty queue. And there's a pretty simple way to implement this, which is using a list. So a standard basic implementation of a queue just consists of the representation type being a list, and you start with an empty list for the empty queue, and you append to the end, and I don't know. It's a pretty basic implementation of queues, but it's obviously not so efficient. Another implementation that you might be familiar with is sometimes called a batched queue, the idea being that you implement a queue using a pair of lists, and you don't have to worry too much about the details of the implementation. Maybe one high-level thing to know is you NQ to the first list and you DQ from the second, unless the second is empty, in which case you reverse the first list and move it to the second. So, all right, if we had these two implementations, we can think about how they relate to each other, and we can, first, I want to pull up this quote from Liskov and Zillies back in the 70s, where they were thinking about modularity. And they said that when a programmer makes use of an abstract data object, you should only be concerned with the behavior that object exhibits. So surely then, I should be able to verify code about both list queue and batch queue without worrying which one I chose. So okay, here are a couple client programs, C1 and C2. They both take in an implementation of the queue library, and they compute a number as well as a queue using that library. And the first way that you would do this is by starting with an empty queue, NQing the number 1, NQing the number 2, and then DQing. Another way that you could compute the same results, ideally, would be the second client, C2, where you just say, well, I know the number is always going to be 1, and the remaining queue is going to be a queue just containing the number 2. So we'll start with an empty queue and NQ2. So the intended theorem, if we're satisfying the modularity principle that Liskov and Zillies were thinking about, should be that no matter which queue implementation you pick, no matter what library you choose, or what implementation of the interface you choose, then C1 and C2 should agree. In other words, if you're in the middle of a big verification about some algorithm involving queues, you ought to be able to swap out the more complicated C1 for the simpler C2. And indeed, it is true that if you plug in the list queue implementation, both of these things return the number 1 and give you the singleton list 2 representing the queue containing the number 2. But unfortunately, this isn't literally true when you use batched queues. So you'll notice if I use the first client, I'll end up with the number 2 in the second list versus the second C2 client will end up with the number 2 in the first list. So even though these are pretty similar, they're both queues storing the number 2, if I'm in dependent type theory and trying to do verification, those are different values, and I can't just plug one for the other. So this is, by the way, a really common pattern. Every time you're doing some efficient implementation of a data structure, you always pick some underlying representation tricks that should not be exposed to the client and are adding additional information for the purpose of efficiency. For example, when you implement dictionaries using a balanced tree scheme, the union function satisfies like no good properties. It's not associative, it's not commutative, even though clients ought to think that it is. So the reason is the underlying tree shape won't be the same. Basically, anytime you do any data structures, all the reasoning properties don't literally hold, which makes modular verification in dependent type theory a difficult challenge. So the goal that we're going to now think about is a notion of semantic modularity as opposed to a syntactic notion of modularity. So commonly, if you're used to using a language like ML, you're used to some tools for modularity being afforded using modules, where you restrict what clients can physically see using something like existential types. And that's a syntactic discipline for separating information. But when you're doing verification, it's really important that you have a way of hiding information and proving semantically that you won't reveal it. That way, verification clients can see some of the information, but not all of it. So, okay, the big question that we're going to try to answer, in other words, is how can we reconcile modularity with verification? All right, so the first thing I need to tell you about as background is something called an abstraction function. This is something that Tony Hoare came up with back in 1972. I kind of spliced my own example into his quote. I hope that's okay. But he says, modulo this example, he says that for proving correctness of this batched NQ implementation, you should define the relationship between the abstract space of list queues, in which list queues NQ is written, and the space batched queue batch.x of the concrete representation. And you should do that by giving an abstraction function alpha from the batch queue implementation type to the list queue specification type. The idea is that you can't just verify batch queue's correctness on its own terms. You have to come up with some specification that clients should think about, which is list queue in this case. So once you give this abstraction function alpha, you have to prove a couple equations. So these are some commutative squares that represent equations. You should just think that if you go from the top left corner to the bottom left corner on either route, they should be the same. And the idea is that you have one of these equations per operation, showing that the batch queue operations and the list queue operations are compatible up to this abstraction function alpha that converts you from the former to the latter. So in this case, for those of you playing along with this example, the abstraction function is this thing. Don't worry about the particulars if that's not something that you know about already. OK, so back to these two clients from before. I want to point out that even though it wasn't literally the case that the two clients agree on batch queues, if you take out the queues that we were noting aren't literally equal and you apply the abstraction function, you end up with the same list that's just a singleton list containing the number 2. So in a sense, we want to verify not literally how these things are equal, but we want to verify up to the abstraction function alpha. So the principle is going to be, when you're doing verification as a client, you don't want to verify BQ's data literally, but you want to verify it at the level of LQ, the list-based queue specification, and you get there by using alpha. So this is the big idea from this work. We're going to try to build all three of these components into a type. And this sounds a little bit intimidating at first, but we're going to try to say, not only should your implementation type contain batchq.x, that pair of lists type for efficiency, but you should also build in the specification type listq.x, and you should build in the transformation alpha that gets you from the implementation to the specification. So all this data is going to be built into a single type. And here's a quick diagram explaining what that means, but we'll get into more details shortly. The idea is going to be that on the left we have batchq.x on the top and listq.x on the bottom with the abstraction function. All of that is going to fit into this hybrid implementation that I'll call blq.x for batched and listq type. And when you implement something like blq.empty from unit to blq.x, then that's going to, under the hood, consist of implementing batchq's empty function on the top and listq's empty function on the bottom, such that you prove that they cohere up to the abstraction function. So we're going to take this tall picture and we're going to compress it down a little bit, where we're keeping track of both the top and the bottom simultaneously. In other words, we mediate between implementation on the top and specification on the bottom. So OK, let me tell you how we're going to accomplish this, and we can make this a little bit more tangible. So we're going to use this thing called the abstract phase, which is a synthetic phase distinction. That fancy terminology really means I'm going to add a proposition to my language. So really, this is the only change I'm making to my univalent dependent type theory. By the way, we're there. So we're going to add a single proposition called abs that's supposed to tell you that you're in the abstract phase. So in other words, it means that if abs is in your context, you can't prove it in general because it's an abstract unknown proposition. But if you could assume if you assume that abs is in your context, you should think that you're only looking at the specification and you ignored implementation details. So for example, abstractly, which means assuming abs holds, then you should hope that the batched list queue implementation simplifies down to just the specification. So it ignores all those pesky implementation details. So again, diagrammatically, what this looks like is I claimed we were going to build batched queue and list queue and alpha into a single type. But if you assume this abstract phase holds, it's going to let you isolate just the bottom part. So it's going to let you isolate just the specification, which is good for verification. As we saw, list queues are well behaved for that purpose. So using this abs proposition, we can define two modalities. So we're importing these from prior work. I won't tell you the definitions, but they're not too bad. The concrete modality, which is this black circle, marks data as private, which means it's only important for efficiency reasons. And the abstract modality, which is this white circle, marks data as public, or available only for the purpose of verification. So using these modalities, we can mark the data we have with its purpose. So we can say that it's important for running the real code, or it's only important for verification. And using this construction that's called gluing, given as a special case here for this example, we can concoct this blq.x hybrid implementation. And here's how we do it. We say that batched and list queue hybrids consist of, an element of this type consists of a pair of a batched queue and a list queue, where the batched queue, you'll see, is annotated with that black circle concrete modality because the batched queue is the efficient implementation, And the list queue is annotated with this white circle because we're only interested in the list part for verification purposes. So we annotate each element of the pair with its purpose. And then there's a side condition where you have to make sure that up to some modal primitives, alpha of the batch queue is the list queue. So you make sure that the batch queue and the list queue cohere up to this abstraction function alpha. So in this way, we're building all of the data of the batch queue, the list queue, and the abstraction function into a type. You can see all three of those components in there. So what's good about this type is the following. Well, if we use the lemma that says that in the abstract phase, the concrete modality disintegrates, it turns into the unit type, and the abstract modality on the list queue evaporates, then you might notice that, well, abstractly, batched list queue turns into pairs of unit, which is because the batched queue type under this modality disintegrated down to the unit type. And the second component just consists of a list. So really, I'm storing pairs of units and lists, which up to a notion of equivalence is just the same thing as storing a list. So in this way, we're able to concoct this type blq.x that achieves the intended goal. It's a hybrid of batch queues and list queues, such that if you want to isolate the specification part for verification purposes using the abstract phase, it does indeed degenerate to lists. Okay, so let's think about how you'd write code on this thing. In particular, let's try to do the simplest possible example of batched list queue's empty function. So empty is going to be a function that goes from unit to this hybrid BLQ type. And just let me expand that out. That's the same thing as we had on the previous slide. The way that I'll implement this is by giving a pair of a batched queue and a list queue. And in fact, I'll just use the batched queue empty and the list queue empty that come equipped with the batched queue and list queue implementations. So I do have to mark both of these with their appropriate modal primitives, but anyway, that's just making sure that things type check. That's making sure that the annotations indicate whether something's important for efficiency or for specification. So once I pick this pair, there is this side condition that means I have to show that these things cohere up to the abstraction function, which if I just plug those things into that equation, says I have to verify this, which, okay, simplifies down immediately to this thing. And you might notice that there are some modal primitives on the outside, but it would suffice to prove this by using congruence with respect to those modal primitives, that you just have to show alpha of batched queues empty is the same thing as list queues empty, which is in fact exactly the square that we started off saying is part of an abstraction function verification. So we already proved this, and we were able to assemble the data of batch queue empty, list queue empty, and the proof of coherence into this one operation. So this was the intended goal. I won't show you the other operations, but they're pretty similar. So what's the payoff of this? Why did we do all this? Well, we get a principle of non-interference, and this is something that was anticipated by Dijkstra in 1965, if you can believe it. So Dijkstra back then was thinking about the principle of non-interference, as he called it, which is that the correct working can be established by taking into account the exterior specification only, and not the particulars of the interior construction. Here we're calling exterior abstract and interior concrete. So, by the way, this notion of non-interference in our work we observed is the same thing as an information flow kind of non-interference, which is an amazing confluence of terms. So let's see what this looks like in practice. If we define queues, finally, by the way, at the beginning I defined this interface to be pre-queues because there was no restriction that these things behaved like queues. But in reality, we want to restrict these pre-queues such that they behave like queues. And we can do that by considering all of the pre-queues that abstractly are equal to list-based queues. So this gives us a notion of pre-queue that actually has the intended semantics. We can note that, for example, batched list queue hybrid has this interface because indeed, as we showed just a second ago, abstractly it's the same as list-based queues. So now if we bring our clients forward from way back when, and we have them take in queues rather than pre-queues, which come with this restriction that abstractly they're known to be list-based queues, we can prove the following theorem, which is that, in fact, it is true that for all implementations of the queue library, abstractly, C1 and C2 agree. And the proof is a little silly. I included it on one line. It's really just any possible implementation of queues is abstractly list queue, by definition. So if we restrict the intended semantics to be list queue, which we can now do using this abstract phase, then this principle of modularity falls right out. So we reified this principle that Dijkstra was hoping for as a theorem. Okay, so This not only applies to the situation of usual dependent type theory verification, but it also upgrades to cost analysis. So even back in 1995, Stepanov, who developed a lot of the C++ standard library, was thinking about modularity and its connections to efficiency, where he was saying that you can't have interchangeable modules unless the modules share similar complexity behavior, so you have to have complexity assertions as part of the interface. The idea being, if you had one module that was very efficient and you swapped it out for an inefficient one, surely that's something that a client would notice, and therefore it's a little bit anti-modular. So if we want to think about such things, we have to switch to a dependent type theory that enables cost analysis, and that's something that my group has been working on for the past few years. So we have this tool called CAF, which is a dependent type theory for cost analysis that includes a monadic cost effect, which is written as charge C. That just means adding C units of cost to a program. So in particular, you're able to return values into this monad, and you're able to charge C on top of something that's already monadic. And we also had this thing a couple years ago at POPL called decaf, which extends CAF with inequality of costs as a simple directed type theory, where inequality means, well, E is less than or equal to E prime when E and E prime share the same behavior, but E might have lower cost than E prime. So that's your one-slide introduction to our past few years of research. Okay, if we add this monad on the output of the pre-Q operations, so you can have effects in empty NQ and DQ, we can now annotate batch Q so it actually has cost. So we can pick a cost model to be the number of cons nodes created. Here we'll therefore charge 1 on the NQ function because we always create a new cons node. And DQ, we will sometimes charge 0 in the common case, but occasionally in this expensive case, we'll charge linearly much cost because we have to create new cons nodes when reversing the list. So now it remains to annotate list-based queues so that they can match the batch queues in order to complete this analogy with the previous work. So if we had to come up with some list queue that matched batch queue, some public-facing specification that included cost, well, I guess you can just pick that the cost of list-based NQ should be 1. So list queue is now serving as some sort of cost-aware interface for batch queue. And in fact, this equation will hold if you pick 1 because the batch queue always took 1 cost on NQ. What's the situation for DQ though? Unfortunately, we can't always know what the cost of a DQ is going to be because sometimes it's 0 and sometimes it's linear depending on some internal implementation details that we can't possibly see at the level of lists. So what we can do is we can pick an admittedly pessimistic upper bound by picking linear cost for DQ and saying that this square laxly commutes with this inequality. So if we can build in this notion of inequality, then we can represent upper bounds as cost interfaces. And this is extremely important because basically all the time, once again, if you ever implement a data structure, under the hood, the cost will be something that you can't literally export. Any kind of data structure uses some private implementation details to incur cost, and you can't tell exactly how much from the implementation. Always you have to give some upper bound. So in order to include these squares with inequality, we introduced this novel ceiling effect. And ceiling lets you combine two programs such that you abstractly pretend you're the upper bound, but you also keep track of this implementation that has the intended cost. So here, you can seal some program E against some program E sub circle, where that's the abstract upper bound. And as long as you prove that they're upper bounded, you can consolidate these things into a program that represents them both. So for example, if you had this inequality square where the top edge, the real implementation was costing 2, and just as a contrived example, the specification wants to upper bound that with 3, then you can write this example program by sealing 2 cost with 3 cost. So there's now the question of how you would do this in the bigger case of batch Q DQ being upper bounded by list Q DQ, and morally you just bound batch Q DQ by list Q DQ and seal them, but actually there's some more complexity going on there. This doesn't literally type check, so see the paper for more details. All right. So let me conclude by first saying what we did in this work is we used 4 key techniques, which are univalence, synthetic phase distinctions, modalities, and CAF, to talk about modularity, including cost. And of course, we're building on a mountain of related work. I can't talk about that at this level, so please see the paper. We have a whole comparison, but we build on a long tradition of modularity, and we have really cool connections, I think, to a lot of prior work. So let me summarize what we did. We noticed that we can represent abstract models and abstraction functions inside of types, so we can not just choose the efficient implementation type, but also some other aspects for verification. And that lets us realize these verification level properties, and it gives us a notion of semantic modularity, where you have to prove you don't reveal too much information. And this is, by the way, a pretty unobtrusive change, because all you had to do was postulate a single new proposition in your type theory. So you can use this today. In fact, it's implemented in cubical agda in our artifact. Once we had this abstract phase, we implemented a little standard library based on prior work, which is the concrete and abstract modalities and gluing, which let us cook up this hybrid implementation. And then from that hybrid implementation, we noticed that we got a non-interference and modularity principle, which is not just a principle like it has been historically, but a provable theorem that's part of our standard library. And that gives you a notion of modular verification. And finally, we extended to the domain of cost by allowing you to upper bound an implementation by a specification using this ceiling effect. All right, well, I think that's all the time I got, so I'm happy to take some questions. Thanks.
So would you say a few more words on how univalence is used in your stuff?
Yes, so you might have noticed that I said BLQ is equal to LQ, and of course that's not literally going to be true. That's going to be some kind of univalent equality. So you can prove they're equivalent, but it's, yeah, you're using equivalence. We also use the structure identity principle to replace batch list queues with list queues, for example.
That's very nice. I come to it from the context of having spent way too long writing abstraction functions from bits of system C code to specifications in other ad hoc, nicer languages. And it's kind of obvious after doing that for a while that it would be nice to have tighter connections between these things.
Yeah.
So I spent the whole talk trying to understand whether conceptualizing in terms of some integrated language with modalities for a phase distinction would help, or how it would help, and I don't understand.
Yeah, so I guess we're trying to accomplish exactly what you described, which is take all of these abstraction functions that have been verified over a long time and consolidate that data into a uniform type theoretic framework that affords you principles like modularity. So when you build the abstraction function into your type theory, then you're guaranteed this notion of non-interference and modularity that we looked at, because you are treating this abstraction function as a distinct first-class object. So rather than just another function, it's built into your type. And the fact that it's connected with this abstract phase proposition lets you guarantee certain modularity principles. So it's a way of building all of the data that we have before about abstraction functions into the language in such a way that affords these principles.
Distinction is kind of built into the ad hoc separation between two different languages that's common in verification tools. So
let's take it offline, because we have lots of questions.
Sure, very nice talk.
Thanks.
I'm wondering about amortized costs, because that's really what you're getting from the queue, right?
Yep, so admittedly I picked a pretty pessimistic upper bound, but our upcoming work is about building this up to amortized interfaces. So I'll have to ask you to stay tuned for that, but I think we have something cool.
Yes, very nice talk. I'm wondering whether this would work if you, rather than had abstraction functions, used abstraction relations or something a little bit more flexible.
Great. So that's a good point. This does work with relations. There's kind of a directedness to it, though. So you always do, at least we observe in this work, it seems like you always want to have some kind of directedness where you can take something concrete and make it abstract. If you happen to have two concrete things that you wanted to relate, one way that you can do this is by connecting them both to some common target. So if you had batched queues and then, I don't know, real-time queues, then you could connect both of them to lists, and the relation between those two things would be that they map down to the same list abstractly. And you can always do this. If you have any relation, you can always construct some abstract model that they'll share by taking like the push out of the relation. So you take, well, whatever. There's some construction you can do to make this fully general, but this is compatible with relations. Is that good?
Okay, let's have the next speaker set up, and we have time for one or two more questions.
Thank you for the talk and the example that you gave of the worst case complexity. It just so happened that the complexity you gave was also the one of the concrete list specification.
That's true.
Is this a restriction, or would it be possible to give a lower cost there, which is not fulfilled by the specification?
Yeah, so you can definitely give a lower cost. I picked this batch queue example just because it's easy to talk about at the level of this talk, but there's no requirement that the model coheres with what the list is doing in this example. It just so happens that we had a coherence there. But as another question asked, you would probably want to say that the batch QDQ has constant amortized cost anyway, and modulo the fact that we don't have amortization in this work yet, you could totally say that it has constant cost. It's just...
Well, I was more thinking of a case where the specification has, for example, in your case, linear complexity, but we know that there is an log n complexity for an actual good implementation. And then we would want to say, well, it's easier to think in terms of lists, but in actuality, we want something that is logarithmic.
That's exactly what's happening here. So the annotations you put on the specification are usually not realistic to the specification code. So you should think of the specification like math that you're using for analysis purposes. So if you had some log n implementation, you can still annotate the list-based specification with log n, even if that's not a realistic cost model, because you should only be putting a realistic cost model on the implementation, not necessarily on the spec, which is just math. Does that make sense?
Thank you.
Thanks.